Please start.
Thank you. Okay, and thanks for the organizer for this opportunity to comment more about my current research, mainly with Nico Yunes and Carlos Opuerta. So we're going to switch gears here a little bit, stop talking about comparable mass black holes with LIGO, those interesting talks that we just heard, and we're going to move to lower frequencies to study EMRIs, extreme mass radiation spirals, with Lisa. And then I'm going to talk about work that is in progress and something that is related to non-integrability. Okay, so we know that the dynamics of binary systems in GR are extremely rich, but unlike Keplerian orbits, bound Kerr geodesics are triperiodic, and that means that they are described by three frequencies, the ones I'm showing here, associated to the radial, polar, and azimuthal directions of the motion. And since the geodesics equation in Kerr are integrable, that is that we have enough constants of the motion for the degrees of freedom, we can always introduce a set of action variables, angles, and parameterize the motion also in a torus and start also thinking about this in phase space easier. So in this case, the conjugate variables are functions of the constants of the motion. And what I'm going to talk about in this talk is related to a particular case. So when two of these frequencies became what is known commensurate, that is that the ratio is a rational number, a resonance can happen, and then that might introduce a very distinct change in the evolution of the dynamics. And then this condition is known as the resonance condition. And since we are left with just 2 degrees of freedom, we can see that from the metric. Our metric just depends on R and theta. These are going to be the frequencies that are most important. So when this happens, the phase space trajectories will not densely fill this torus in phase space. So they will just create now a choreography, a sort of Lissajous type of figure, if you wish. And then the motion is becomes a little bit more interesting because it's not filling densely this torus. The existence of these resonances is very important for both integrable and non-integrable systems. And in this talk, I will mainly just talk about the consequences for those resonance when the system is non-integrable. And that means that I will not talk necessarily about Kerr, because in Kerr, these effects that I'm going to show don't happen. So in particular, what I'm going to show is that it has been known that under a perturbation, according to Cam theorem, some of these torus that for each of those that I'm showing here are for different initial conditions. And then here I'm making in that blue plane a cut through phase space. I'll show that in a second with more details. So what happened is like Cam theorem tell us that when there is a close to those resonances, when we arrive to these resonant conditions, some of those tori will break. And that's because of the presence of a perturbation. And in fact, I'm seeing in another way, what Cam actually is saying is that for 2 degrees of systems, the condition to preserve that torus, and again, remember that this nice set of nested tori structure happens in integrable systems. If there's a perturbation, they will break. And then we can see that the ones that will remain or will preserve under a perturbation are given by this condition, sort of that condition, where K and epsilon are the depends on the characteristic of the perturbation or the strengths. Epsilon will characterize how big our perturbation is. And then this says that the ones that will survive will go in this way. So as you can see, there will be a hierarchy in this expression, meaning that the lower frequencies, the ones that have a low m and n as integers, are the ones that are going to perhaps break easier. If you have these numbers very large, this number goes to 0, and then those are the ones that are difficult to break. Meaning that under a perturbation, we know that the low frequencies, like, I don't know, 1, 2, 1, 3, 2/3, are the most susceptible to affect. And then they're in those locations, and in particular in those resonance, is where things might change. So that means that for non-integrable solutions or perturbation of unintegrable systems, we might have a very interesting dynamics that we can search for. And that's what I'm going to address in this talk. And in particular, in the context of a small black hole, maybe you can see it here, falling into a supermassive black hole. Okay, so just a little bit more in detail, because we will use this technique over my talk, is like, let's study this small black hole falling into a supermassive black hole. And then I'm going to make, if you remember, there was a cut in that tori structure, that was the blue plane. So whenever my particle crosses the equatorial plane, I'm going to record its position and its momenta, PR. And then the particle continues evolving. It goes another time. It pierces again the equatorial plane and does that, and it does this. So this is the way that we can create what is called the Poincare surface of section. So if you remember, for each initial condition, we can create one of these nice surfaces. And then you do this for sufficiently enough piercings of this structure, and then you form what is called the Poincare surface of section, which is another way to look the dynamics of the system. You can play, if you go to Leo's webpage and create this for different initial conditions and do that actually in a dynamical way, very interesting with this Java application that Leo created. Okay, so let's step back and then see what I have been talking. We have an EMRI. It will just go around the supermassive black hole in a sort of geodesic. We're treating the small particle as a geodesic. We can study the dynamics of the system by just looking at the trajectories. But what I'm saying is, like, we can also study that from the phase space. So if we perturb the system, at least two things might happen. Well, one, some of those trajectories, they will not see the perturbation. Another ones, they will just be slightly pushed because the existence of now hyperbolic points in phase space. So those trajectories are trying to avoid those spaces. And then other trajectories might even break and form what is called Birkhoff islands. So now we have here stable points. And in these locations, we might have now hyperelliptic points. And this is guaranteed that the phase space will break in an even way. You will create N. In this case, I'm showing a 2-3 resonance where we are seeing three set of islands, and then we have these three stable points and then three unstable points. So a way to characterize this, because these features might be very small, is through what is something that is called the rotation number. So in this case, we choose a point that I'll call the invariant point. It's the point in the trajectory that is always piercing this phase space at PR equals 0. And from that, I'm going to just draw one of those Poincare surfaces of section. Remember, this is just one initial condition for the motion. And if you remember how this surface is created, is by piercing, successive piercings. So let's say this is the first piercing of my trajectory. I create this vector, then this is another one, I create this vector, and then I can measure this angle. So if I do this for many, many oscillations, I can create what is called this sort of a statistic, which is the rotation number. And I can plot that rotation number as a function of different initial conditions. And the results are something like this. So what you see is, like, if your system is integrable, as is Kerr, you will always find that this rotation number will be monotonically increasing or decreasing, and nothing is happening. But as soon as you arrive to a chaotic region, you will find a plateau. And then, or if your system is slightly perturbed, you find an abrupt change in this rotation number. So what I'm saying, just to summarize so far, we have the trajectory in physical space. We can go to phase space, look at these signatures, will reveal signal that the system is not integrable, but I can also extrapolate all that information to this one-dimensional curve. And whenever I see this type of signatures, like a plateau or an abrupt change, that signals non-integrability, and that's what I'm meaning by chaos. I'm now mentioning all these tools and techniques is because this rotation number is proportional to the ratio of these two fundamental frequencies, meaning that, for example, here, as I said, I'm showing a 2-3 resonance, and then for that particular system, which is just an example, it's a toy, you see that in this case, I find a plateau, meaning that the particle is moving through, let's say, these Birkhoff islands, and then I know that at least this ratio of the resonance, they got locked, at least, meaning that all the particles that have initial conditions in these islands will have exactly the same ratio of these two fundamental frequencies, okay? So that means that this is a cheap sort of way to look for symmetries in a theory. So let me just put an example, dynamical Chern-Simons, which is defined by modifying this Hilbert-Einstein action by adding a pseudo-scalar, which is going to be coupled with this coupling parameter. Here we have the Riemann and its dual, and in this way is a quadratic term called the Pontiagram term. Here I'll have the kinetic for my pseudo field, and then if I have matter in this field. So in vacuum, and if I neglect this kinetic term, this is how this theory will be described. And this is a well-defined, well-motivated theory of gravity. If you want to know what I mean precisely by well-motivated, I can talk later. But the point is that the solutions in this theory had just been found either in the slowly rotating limit or in the extremal approximation. What it means is basically is that you are seeing this. Now we can cast related to what I just said, is like it's going to be Kerr, which is integrable. None of those features I show will be presented here, plus a modification. Now the question we can ask using the tools I just mentioned is dynamical Chern-Simons an integrable or a non-integrable theory? Meaning that is this adding a perturbation that is non-integrable, or is adding a perturbation to Kerr, which is an integrable system, that is non-integrable? It's easier, instead of seeing this coupling parameter, how the theory is minimally coupled, we can just recast this in a dimensional parameter. So that's the most common term that it's used, and is this zeta. And the point is that the solutions, as I mentioned, are just found in linear in this zeta parameter, and first found in first order to spin, second order to spin, and more recently to fifth order in a spin. So this poses another interesting question is, okay, we want to study dynamical Chern-Simons. We want to know if there is a fourth constant of the motion, something like the Carter-like constant. In this paper, this in 2012, they show that there is not a second Killing rank tensor or a Carter-like constant. The question is, well, maybe there could be another symmetry. This is a way that from dynamical systems, we can study this theory and understand its phase space. But then the question is, how should we treat this part? Because we know that if we have an integrable system and we perturb it, these type of features can appear. But now the question here is like, okay, we don't know the full solution. So maybe if we see chaos, it could be because we don't have the full solution, meaning that I don't have the solution to all the orders in a spin. So chaos might be related to the fact that I don't have the full solution, or I can restomp the solution and think about just this in a particular way. So keeping that in mind, led us to study actually what will be the behavior of Kerr when it's not fully restored, or when we have the whole order of Kerr. And just as a note, if you want to know like the most stringent constraint in this theory, we put it in a recent paper using LIGO and NICER data. So we use the neutron star, these neutron star observations with LIGO, and also with LIGO for the canonical 1.4 solar masses. So using a multi-messenger test that we propose, we put a very stringent constraint to this theory. Okay, so as I said, it's important to study slowly rotating Kerr. So if we go to slowly rotating Kerr, let's say to second order, this is what you will find, meaning that it looks like it's non-integrable because we are finding these Birkhoff islands. That's fine because this system is very interesting. It's bounded from the left, from Schwarzschild, that is integrable. And if you start adding all the orders of the spin, you will arrive to Kerr, which is again fully integrable due to this fourth constant of the motion, the Carter constant, but everything in between will not be integrable. And if you are at second order, you find this Birkhoff islands. And again, if we look this in this one-dimensional curve, you find that as these little locations, you will find a plateau. Okay, that's fine. Now, if you go to higher order, fourth order, you don't broke your tori, you just deform it, and then you don't expect to see a plateau, you expect to see that rapid change in this curve. Okay, so this was our first, let's say, approach to this problem, to study dynamical Chern-Simons, because we know how to characterize the appearance of chaos when we don't have a full solution. So based on this, we can now go and study a little bit more safely in a dynamical system method how this behaves in Chern-Simons. And what we found is that this rotation number is smooth again for Kerr, so that's fine when this coupling constant is 0. But as soon as you start increasing this coupling constant, you find these abrupt changes. But now again, the question is, okay, are these changes coming because you don't have the full solution, or because dynamical Chern-Simons doesn't even have a fourth constant of the motion? So what we did is like we studied this numerically extensively, and for example found that if you have your solution to second order, okay, you found this abrupt change in the frequencies, but as soon as you start making your solution more precise, let's say you go now to fifth order, this signatures shrink. And that allow us to conjecture that the exact dynamical Chern-Simons metric possesses or has a fourth constant of the motion. This was done numerically extensively for many cases, and this was generically what we found. And remember that the solution is just known to fifth order so far. However, more recently, it was conjectured the opposite, that the solution doesn't have a fourth constant of the motion. And this is a very interesting work done by Caroline Owen mainly. And then what she did was a tour de force. She computed or tried to understand if there were independent killing tensors up to 6th rank, and she couldn't find anything. So she proved that at least to 6th order and 6th rank killing tensors, there is no fourth constant of the motion. She couldn't also prove that it doesn't exist, or that it does exist, but it seems like that. So we have this conjecture. So this one was done numerically, and this was done analytically. However, this analysis is way more robust. It's analytical, so it seems that it doesn't have a fourth constant of the motion. It's not that she couldn't prove it like for 7 or to all killing tensor rank, but the point is that this is really robust. And what we start thinking after her work is that maybe these features that I show here actually will settle to a minimum. So if you, let's say, have the full solution, maybe this chaos shrinks, but then it stays like that. So this is a way that we can reconcile these results, because this, as I said, ours were numerical. But what is funny is that Nico Younes is in both results, so it doesn't matter if there is a fourth constant of the motion in DCS or it's not, he will always win because he is in both conjectures. So you can study this type of systems for order 1. So what I want to show is, for example, this is another case where you just study these geodesics, which we, in a very specific scenario called bumpy black holes, where you can keep and control modification. So in this case, I'm showing a prolate source. We show that in some cases, frame dragging effects might diminish the appearance of chaos. And you can even quantify this by study how many degrees of freedom your solution has in phase space and how much is proving this. But I want to show this just because in this example, I'm showing, for example, again, the pointed surface of section. The red one, this condition is in this chaotic C. You move a little bit in radius and you ended up in a cam curve that is not broken, so it's completely smooth and their chaos is not seen. But as you can see, from this location to the other one, one is chaotic, the other one is not. And now, if you look this, you create, I'll show you in a second how we create this and gravitational waveforms for these EMRI systems. It's not easy to see in the time domain what chaos means for gravitational waves. So you see this one, the blue one is the chaotic one, and then here the orange one is the non-chaotic. And as you can see from the time frequency, you cannot see much. But as soon as you see this in the frequency domain, you see that the chaotic one shows this forest of frequencies. Here it's an EMRI, so it's extremely, it could be eccentric, inclined, it's very like crazy. That's why you see a lot of like structure in this Fourier space. But then the chaotic one shows this like sort of forest of multi-frequencies around the main ones. So actually, if we're able to see this in frequency, then you will definitely see which one is chaotic and which one is not. And again, as I said in this work, we showed that for a particular solution, you can show that frame dragging effects can diminish chaos. And this is also an open question. This is not known. We don't know if what are the effects of frame dragging to chaos. You can see other examples. It has been shown actually many years ago in Manko-Novikov solutions, in particular in these two very nice papers. They also show like this multi-frequency will appear. Okay, so the question is, all these effects are too theoretical. Should we care about them? Are they going to be observable? So let me discuss this now. What I just showed you so far is just geodesics. I have a solution. We can study the dynamics of that solution. And based on that, for example, look for symmetries and try to understand and characterize the dynamical system. But again, if we want to observe this through gravitational waves, we have to add somehow an in-spiral. And then, as I said at the beginning of the talk, we are interested in this approach because you can model the small black hole, at least to first approximation. as a geodesic in the space-time of the big one. And the idea would be to observe this using LISA. That hopefully will fly in around 10 years. But for that, of course, you need a radiation reaction. You need it to radiate, which is something that has been lost in all the slides that I just showed you. So you can study the trajectory of the particle, and this is, let me just go over like what people have done in the past years to produce these in spirals in EMRI, at least to first approximation. You can compute the trajectory of your particle, and then in a multiple formula, this is just one approach, then get your waveform. And I'm showing all these equations just to show you that actually the only thing you need in this approach, which is one that is not completely, let's say, perfect, it has a lot of approximation, but at least it captures all the qualitative features that we might need to study this problem, is that you just need the trajectory of your particle. So what people have done is adding this force, and then they do these radiative effects by adding post-Newtonian terms to the evolution. So you go and compute Einsteinian post-Newtonian terms for the flux, energy, and angular momentum. You put them here, you solve this equation, and then through this method, you just compute, let's say, the first mass multiple moment and the first current multiple moment, and get an approximate waveform for the solution. But this one indeed has an in-spiral. So this has been done. For example, as I said, you can study the trajectory, and in a seminal work by these people, they study in the method I just showed in the previous slide, what's going to happen to the frequencies of the trajectory. So remember, they didn't compute the gravitational waves per se. They computed in this way. They have an in-spiral, but they analyze in Fourier space the trajectory R and theta. That's not an observable, but still this is a seminal work. This was the first time this was done to show that actually it's exactly like that. If your solution starts at a particular condition, it will evolve through a resonance. These frequencies will get locked, and then your system will live. What does it mean? It's like if we are observing a system that is evolving, and then at some point hits a resonance, you might see they got locked, and then they will leave the resonance. So this might, and this is what they claim at that point, this is a smoking gun for non-integrability. But remember, this is coming from the non-conservative part of the theory. That is your theory, your metric. This is not a radiation reaction effect, as I'll show in a second. And more recently, again, in a very interesting PRL, they show, for example, if you have an integrable system, you will see one of these frequencies in the gravitational waves. Now, this is from the observable, actually. You just compute this periodogram. This is time or frequency. And then maybe you can recall this from the LIGO periodograms, where you see your system evolving like whoop, and then it merges. This is something like that. But then, as you can see, the evolution for EMRIs is extremely slowly. And then this is just one of this. If you remember the other multi-peak frequency I'm showing you, this is the strongest one. So you just see if your system is integrable, it's just evolving in frequency. But then when there is chaos, boom, you found a glitch. And this is a very interesting feature, meaning that, again, this one was from the trajectory by studying the Fourier of the trajectory, R and theta. But this one is indeed directly from the observable, the gravitational waves. And then this is very nice. It's a feature that you can find. And these examples were shown actually in Manko-Novikov. This one is a Johansen, one is a particular bumpy metric that is integrable for the condition they show. And this one is in this metric that they propose in this paper, which actually was designed to break integrability. Okay, and that's why they have here a parameter that you can just tune and make the system not integrable. And that's the example they show for these seminal works. And they use linearized Einsteinian adiabatic fluxes. So these solutions, for in particular these ones, might not be necessarily be described within GR, but again, we don't know what's the radiation reaction in any other theory, so it makes a lot of sense to actually put Einsteinian adiabatic fluxes. Okay, so let me just summarize so far what I have just said is we can go from the trajectory, we can study phase space, we understand more or less what are the features of chaos, at least in phase space. Now the question is, this is observable, and then these people say, yes, it might be observable if you can see this in the gravitational wave, and perhaps it's a glitch. So as it was said in the previous talk, like by Constantino, if you want to really capture features, you need a model. And then the question is, can we build a model? But then Again, as I said, the other solutions were shown in Mankonovikov or in bumpy metrics. And in this previous paper with Nico and collaborators, we found you don't have to go that far to look for these features. So for example, the slowly rotating Kerr indeed already shows these signatures. So in the sense, we can truncate Kerr to second order in spin, and still you will find the solutions. And again, this is without radiation reaction. You just characterize different initial conditions that give you confined motion. And then the question is, okay, if we start in this condition A, we will evolve through this, and maybe let us use again the same approach and build a model. So that's what I'm going to show you in the next slide. So we compute these spirals very similarly as has been done before in a Cloggy way, but we made just two changes. One is that we are using the full Kerr fluxes, not linearized as before. And also that means that since we are also evolving the Carter constant, which might not exist for other systems, we are using all these equations. In previous works, theta and FR and F theta are set to 0, so that might change a little bit the situation. And then you get these fluxes, the left-hand side of this equation, from post-Newtonian terms. And your system gets close with this for normalization of the velocity. And then these are the equations that you can solve. And this is exactly what you find even in the slowly rotating Kerr. So you don't have to go that far away to Mankonovikov or something like that. So this system is perhaps a little bit more astrophysical relevant. And then you see it's very similar to what has been shown before. Your frequency is evolving, you arrive to the resonance, boom, a glitch, and then you leave that region in phase space. And then you went through this region using these fluxes that I just showed, that I just described. And this is just initial conditions, a particular spin, a particular semilateral recton, eccentricity, and then a mass ratio for this evolution. And this is in a slowly rotating Kerr. Now, I said we need to build a model. So what I can do is, for example, say, okay, let me study this using Kerr. I have to do something to Kerr to capture this solution. So let me find, up to this point, before chaos is happening in a slowly rotating Kerr, let me find the best initial conditions that can mimic Kerr. And for that, we use this fitting factor, which is something like a dot product between two models, and find the best match. And then that can be done. So note, on the left-hand side, I'm showing a slowly rotating Kerr. On the right-hand side, I'm showing Kerr in blue, slowly rotating Kerr, but up to this point. And as you can see, I can always find a very good match, meaning that we will not be able to distinguish slowly rotating Kerr to Kerr, but mind that these solutions are different. The spin is different, the semilateral recton is different, and the mass ratio is different for that particular evolution. And in particular is because in phase space in both solutions, I'm exploring different spaces. Of course, if I continue this evolution with Kerr, the match will just immediately drop, like really fast, because it's not able to capture this. So I need something to capture this resonance, and that's the model that we want to introduce. And then just by looking this and based on previous works, you can think, okay, maybe I can have Kerr and then put a kick just to enhance those fluxes, and then do something to the solution and see if we can build a model. And the idea goes back to this very interesting paper by Flanagan and Hinderer that they show, okay, if you are studying the frequency ratio, in this case is the opposite as I showed before, that's why the 2/3 is now 3/2 at 1.5. And then they show, okay, if you're studying your system, you don't see anything in this resonance, it's just going through. This is your orbital eccentricity, is decreasing as expected, the inclination angle. But if you study more carefully the fluxes, something happens to the fluxes. And this is what they found. And it could be the changes in the flux because of the resonance within general relativity can be of order unity. So let me stop here a second. What I have been describing so far are conservative modifications, because your theory might not be integrable. That was what I showed before. Here, what I'm showing is that these effects around a resonance where your flux changes are coming because of higher orders in your dissipative terms. And that's what Flanagan and Hinderer found. And a little bit we can understand why these effects actually happen is that if you just use the adiabatic approximation, you will not see these terms. So that's what they mention in these papers, like you need to go post-adiabatic terms, because even within GR, second order terms or higher will cause these effects. And more or less we can heuristically think about this effect like this. And if we can decompose the components of the self-force in Fourier space, you can see that, for example, when M and L are 0, this term is roughly constant. So that's the one that the adiabatic approximation is causing. But for the other terms, when m and n are not equal 0, we have these rapid oscillations. So when you average, which is what we have been doing before for the adiabatic approximations of these EMRIs, in chaos, I'm talking specifically, your fluxes won't see this effect. But at resonances, m and n, this condition, we've hit the resonance condition, this goes to 0, and then those terms start matter. And that's exactly what they found here. So even within GR, now from the dissipative term, you can have also very interesting effects that we have to take into account to study chaos. And that's why when we were seeing that before, we say, okay, maybe with a kick, we can mimic those effects. You might want to see a very recent paper where they study the effect of these resonances and how we can be biased, similar to what Constantino just spoke. But in the case of within GR, and if we have a model, will we be biased if we don't include these resonant effects, or if we are just using adiabatic templates without considering higher order terms. So this is a way to capture this. But again, this is in a different context. This is within general relativity, effects coming from the dissipative part. So these are atypical results, what we found. Again, red is a slowly rotating Kerr, blue is Kerr, now with a kick. And what I mean by that is like the red is just a slowly rotating Kerr with the adiabatic approximation for the fluxes, and blue is Kerr, not integrable, the adiabatic fluxes, but at a particular point, Tk, I'm out in a kick that has a duration of dk, and I'm enhancing E, L, and Q, the fluxes, in a particular way. So the way I did this was doing a full Markov chain Monte Carlo simulation, where I tried to find the best match for T, D, E, L, K. And also remember, this is a different space-time, so I changed eccentricity, simulatus rectum, and the mass ratio to find the best match. And the point is that I couldn't find a good match. So this is not a good model, meaning that I cannot mimic the appearance of chaos by just changing the the dissipative part, by just adding a kick. And this is, I'm not saying this is not a good model. All I'm saying is, like, even I did a full MCMC run over days, try to explore this vast parameter space. Is really huge. It has like from 6 to 8 parameters to explore, and I couldn't find a good match. So maybe this is not a good model. But remember, here I'm just modifying the fluxes, and we know from the one that's chaotic, these effects are not coming from the dissipative part, are coming from the conservative part of the solution. So what I have been working on recently is reviving a work by Nico and Carlos Opuerta, where they describe a new clutching method that it's a little bit different, and it's called a chimera because it puts a lot of things together. And the idea is to solve this Misa TaQuwa equation in a different way. And it's by combining at least two approaches. One is we're still doing black hole perturbation theory, but now we will change, we will not average those fluxes. We will get those fluxes from a multipolar post-Minkowskian formalism. And what it's saying is, like, now you are going to say that your EMRI is moving in a Kerr plus a perturbation. And that perturbation, that regular metric, is a function of certain time asymmetric scalars and potentials. So now it's sort of like you're capturing this at infinity, but now in a post-Minkowskian formalism. This is not post-Newtonian, although at a particular point in a buffer zone, we have to create a match to still produce this evolution, just to get the multiples. But then this one, we're just saying that the gravitational field strength is small for this perturbation. And this is the equation I'm working on at the moment. So I don't have yet results, changing this approximation to try to capture, as I said, non-conservative and conservative effects, both. Perhaps with the chimera, we might be able to do that because of the ways this allows to do that. So just to summarize, I believe we need to understand the astrophysical relevance of these type of effects and glitches that were shown this year nicely by Kokota's group, and determine their detectability and consequences. As I said, it's a good way as a dynamical system theory to actually study a theory per se, to study for symmetries, to characterize phase space. But if we want to observe these effects, we have to disentangle them, and for that have a model. The kicks so far, I couldn't find a good match, meaning that just adding a conservative kick, enhancing the fluxes close to a resonance might not be enough to mimic the appearance of chaos, meaning that it's not just a resonance by the flux that's changing this. So we really have to study the conservative effects and perhaps put them in a more consistent way. And for sure include post-adiabatic terms, because these effects are minuscule, but they will perhaps accumulate in phase over the evolution of the EMRI. And with that, let me again thanks the organizers for giving me this opportunity to talk.
Thank you very much for your interesting talk. Okay, now session is open for question and comments. Please raise your hand. Okay, Sravan, please.
Hi, Alejandro. So thanks for nice talk. And actually, my question is what you have already mentioned in your talk about motivation for your action with Pointryagin number.
You mean for example for DCS?
What is what is the motivation
okay, just
to study with Pointryagin? Yeah.
Okay, that was just an example, and the point, let me just put this reference, is like when you have a theory of gravity, so you can ask, okay, is dissolution parity violating, or we might have that. You can actually study this through dynamical Chern-Simons, and the idea is that this solution has many nice terms. Oh, sorry about that. It's just going too fast. I just want to show this one. And I have listed it. So what I mean by well motivated is like it's solving a problem. So for example, I know from some expansions and the asymmetry of barrier in cosmology, it's solving problems. It passes all the weak tests. So this solution is extremely well constrained. It might be well posed, meaning that you can put this into a computer. And that's actually, I think Constantine mentioned some works by some people at Caltech where they were able to evolve this solution. And interestingly enough, this solution also introduced a new PPN parameter that you can look for in the solar system. For example, it is one that is novel because it's introducing these parity violating terms. So this is what I mean by a well-motivated theory. It's solving a problem. It passes all the tests. You can perhaps put this in a computer because it maybe is well posed, and then you can put this and study that.
You're putting parity violation in gravity, right? So, well, I mean, you are kind of expecting that there should be parity violation in gravity sector, and so you is that your motivation? Because I mean, in particle physics, okay, but for this particular term, Chern-Simons term of gravity, you're putting in your action, right?
Yeah, and that's indeed so. So this will indeed have observational consequences because of how gravitational waves will propagate. It will be a difference between the modes. And I know, for example, in cosmology, even when this theory, you can solve or at least tackle matter and antimatter asymmetry and baryogenesis. So yes, you can, by adding these terms, you can solve a problem and still pass everything else. So yes, it's adding a term because of the pseudoscalar, it's changing this parity thingy. Yes, and that's solving at least a problem in cosmology. And not messing up with everything else. Sorry, and not messing up. Yes.
Okay, but also you have a ghost in your action, right? Because you have this this pseudoscalar is Riemann square. I mean Riemann and the GL of Riemann. So there must be a ghost in the spectrum, right? Because you have like in stellar gravity, but I don't know how the ghost appears here. But in stellar gravity, you have Riemann square. There is, yeah.
No, I don't think these theories have a ghost. We can, if you want, we can discuss this offline, and then I can remember more a little bit this. But I don't think it has a ghost. If maybe someone in the audience is more expert on the theory per se, might help us. But I don't think it has a ghost.
Okay.
Okay, Shinji, please.
Yes. Okay. So nice talk. Thank you. And so I think you consider two possibilities to make the system non-integrable. One is to consider deviation from Kerr, and the second one is to consider deviation from geodesics within GR. And so perhaps you have, I mean, you can distinguish these two cases, and what is your strategy or smoking gun for each of them?
No, that's I believe another problem, in the sense that you can, as you said, yes, one could be because your theory is inheritable, not integrable, but then the other one is, like, as you said, Kerr plus, for example, an environmental effect. And then that's causing a perturbation in your space-time and perhaps leading to these effects. These effects will be very similar. I've also should mention that glitches could appear not just because of chaos or something like this, or the resonance, just because there could be something in the detector that causes a glitch. So the smoking gun here, in the sense, will be if it's associated to these particular resonances and the duration. So that's why we need to build a model to really get the physics from that. But so far, we are not there to really distinguish this from an environmental effect. Then for those steps, we will have to really enhance our models a little bit more.
I see. Yeah. Okay. Thank you.
You're welcome.
Okay. Any other question or comments? Okay. No. Okay. So let's thank Alejandro again. Thank you very much.